Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, it's been great fun so far, and I think we have some great speakers left this afternoon. Our next speaker is Aaron Hertzmann, who is going to show us how to get rid of that annoying camera shake that we all suffer from in almost all of our pictures, especially I certainly are in most of mine. Aaron is here from the University of Toronto, although he's no stranger to this area as well. Aaron?
Right, thanks. So in continuing the tradition, this is also joint work with Rob Fergus. Wait, this one? How do I make it switch to PC3?
PC3 and then hit both screens.
Okay, great. All right, so, and also joint work with other people, but this is really, Rob is the main person on this, and he's starting a faculty position at NYU soon. So, as Michael mentioned, the motivation for this work is the problem of camera shake. It's certainly an experience that lots of people have had, where you go take a picture, especially pictures taken outdoors or at night, and it looks, everything looks fine, and you take a picture and it comes out blurry. This is one example, and our goal is to remove that blur. So this is the result of the algorithm, which I'm going to the result produced by the algorithm, which I will be describing shortly. And so, just to look at the details, this is the input, just a detail of the input image. This is what happens if you simply sharpen the image. You amplify noise, and you get some ghosting artifacts because sharpening isn't really enough to compensate for blur, for motion blur. And this is the result of our method. So this is something which, I've certainly had a lot of experience creating camera shake. When I first bought my first point-and-shoot digital camera, I went abroad and took all these pictures, and so many are blurry just because the resolution of the sensor is very high, the camera is very light, and you just want to take pictures all the time, and you're walking down the street and you see something really cool, take a picture at night, and it comes out blurry, and you can't just go back and try again a lot of times. So that's the issue we want to deal with without additional instrumentation or anything. So just to get a sense of this in more detail, again, our friend Antonio Torralba shows up to help us demonstrate this problem. So here Antonio comes and takes a picture, and it's disappointing. Such a shame it didn't come out so well, and then he has to give up and leave the camera there. So we get this blurry picture as a result. So just to understand what's going on here, we've taken a very high-speed camera and filmed this in slow motion. So you can see exactly what's going on. Again, he walks up and picks up the camera. And then we zoom in. And you think, it seems like an instantaneous process. You press the button and release it, and it's just like a split second. But in reality, it actually, there's a lot going on. So this is obviously a little bit of a caricature, but the point is the camera is open for a little bit of time. Your hand is moving during that time, and so you get blur in the image. And you're sad. Okay. So in this work, we're going to model the blur in the following way. We're given this blurry image, and this is basically all the information we have. We don't really know anything about the camera or anything else but the scene. And we believe, or we're going to pretend that this image was produced by a convolution of some unknown sharp image, like, an image that, had we held a camera still, we would have gotten, together with some blur kernel. And this blur kernel can be viewed as essentially an image of the motion of the camera during the exposure. So this is sort of like the path the camera took. Convolve these two images together, and you should get this one. Now, of course, this model, so the blurry image is our input. We want to get this sharp image as our output. And now, of course, this model is very much an approximation to the real blur process. It doesn't model things like motion of objects in the scene. It doesn't model in-plane rotations of the camera, but for a lot of cases, this will be a sufficient model. Now, there are also lots of other ways to address this camera shake problem. The simplest thing to do is just add a flash to your camera. So it works sometimes, but here, so this is one picture I took with a flash in Tibet. Not a situation. One thing, it felt really obnoxious to use a flash in this, when these like folk dancers were having a public performance. But also, it really changes the content of the scene. It wasn't like this guy's hat was really bright lit. Naturally, it was just the flash was really changing the scene. The other thing you can do is carry a tripod around, which I find also very difficult to do. I don't want to carry a big tripod, but that's also another way to stabilize the camera. There's also been some more recent things. Image stabilizers have now moved into the point-and-shoot market, and they help a lot with certain types of blur within a certain range of motion. They work well. There's been other more experimental things, like you can augment the camera in order to track the motion. So here there's a video camera together with the still image sensor, which is used to estimate the motion of the camera. And there's also other ways to, if you know the motion, to do better deconvolution. So this flutter shutter method can help with a deconvolution step. All these harder methods are really complementary to our own. They help reduce the problem or add information, but they don't really solve the problem always, and they could be used together with our method. The other thing I should say is our method is really designed for cases where you can't augment the camera, like you took a picture 10 years ago or last year, and you don't have the choice of augmenting the camera. So now, people have worked on this problem for many, many years. Actually, there's at least 4 decades of literature on image deblurring, and you might think, well, they should have solved it by now, but it's a really hard problem. And one way of looking at it is that we really have these two images which are being multiplied together, and we want to get them both out. So like a really simple case is, suppose I tell you that 11, somehow I got this number 11, but I got it by multiplying two numbers together. It's not obvious what those numbers are. There's actually an infinite family of solutions which all multiply together to get 11. So just because I tell you the product doesn't mean it's obvious you can figure out what the two numbers multiplied together were. In the case of convolutions, the same situation arises. This blurry image could be the convolution of some blurry scene with a delta point spread function. It could be some other really weird function times a big Gaussian, or it could be this sharp scene times blur kernel. And so there's again an infinite family of solutions that fit the data perfectly, and somehow we need to bias our solution towards the result we want. Another way of saying this is, mathematically, this is an ill-posed problem, but when we as humans look at these images, it's really, really clear which is the right one and which one's the wrong one. So somehow there's some additional thing that we as humans are doing which we haven't figured out how to model yet. So what else can we do? The slide is out of order. As I mentioned, there's a lot of work in this area. I'm just going to skip over that. So the first thing we can do is to consider natural image statistics, and this is exactly the same thing that Fredo talked about earlier. So for this particular image here, and I also should say, Fredo mentioned that if you ask each of these people who worked on that project for an explanation of this regularizer, you get a different answer. And I actually have a different answer. It's more similar to Frank's, actually. If we take this image here and compute gradients and plot a histogram of the magnitudes of the gradients, then we see this very characteristic heavy-tailed distribution. Most gradients are small, like there's a lot of many flat regions, which gives us many small gradients. But there are a bunch of larger edges. There are regions which are not continuous, and so we get these large gradients as well. This is a very non-Gaussian distribution. If the distribution was Gaussian, that would correspond to an image which is smooth everywhere. So Gaussian or quadratic prior is really the wrong thing to do. Now, moreover, if we blur the image, we also change the distribution. The heavy-tailed distribution becomes less heavy-tailed, becomes more compact. And so what we're going to do is fit a distribution to this empirical distribution, actually just a distribution in this one image, and we'll use that as our prior. So this green distribution is the one we happen to fit. And we're using a mixture of Gaussian's model for this distribution, but we could have also fit a log exponential model, and then we would have gotten exactly the prior that Fredo talked about, this gradient of x to the 0.8. And so you can really view, I don't know exactly what number we would have gotten because I haven't actually tried this, but I suspect that that 0.8 may come from precisely fitting this distribution. But that's not the model that we use particularly. Now, there's been quite a bit of work in that exploiting this particular observation over natural images and denoising and inpainting and hole filling and so on. And we're certainly following along this thread. But one big difference between us and the stuff that's been done before is all of these other methods assume that the corruption process is known. So, for example, in the deconvolution work, you assume you know the kernel and then you try to reconstruct the image. Or in super resolution, you assume you know the degree of blur, and then you attempt to reconstruct, well, again, the image. And so our problem is actually more difficult because we don't know the underlying image or the corruption process. So it turns out that if you just do sort of the natural map thing, sort of like what Freddie mentioned, for the problem where you don't know the kernel or the image, then it's not going to work so well. And I wanted to attempt to give a little intuition for why that is. Probably some of you have probably seen versions of this talk before, and I think I very much preach the sort of the Bayesian way of looking at things for getting a lot of information from a little bit of data, but sometimes there's beautiful math behind it, but sometimes it's hard to get an intuition as to why it's really working. So hopefully I can give a little bit, although I don't feel like we have a really complete story here. So let's just consider, just to understand things, a really simple case again, where the case where we have a single measurement, like we measure y equals 11 or something, and we believe that that measurement came from the product of two unknown numbers, b and x. You might think of it as a blur in the kernel, but here they're really just two scalar values which are unknown. And we also assume that there's some noise corrupting the process. And now I tell you we measure y equals 2. So what can you tell me about b and x? Well, so just looking at our model, if we just consider the likelihood of the data, so what I've plotted here is if I consider a possible value of b and x, given that y equals 2, there's a hyperbola of values of b and x that multiply to get to 2. So b could be 1, and x could be 2, or b could be 2, and x could be 1, or any point along this curve in the middle of this curve will exactly fit the data. Now, because we have noise in the problem, we're not constrained to lie precisely on the hyperbola. We could be a little bit off. So that's why this curve is actually a little bit thicker. And one thing to notice here also is that the curve is thicker in this region down here than off in these tails. And so one way of interpreting that is that if I were to interpret this measurement, where y equals 2, as saying, well, let's say I think that means that x equals 10 and b equals 1/10, that solution is a lot less stable to noise. If there's any little bit of error in my measurements, then, or if it turns out, well, I was actually off by a little bit in my measurement of x, then suddenly I have a much worse result. I'm much further from being correct. Okay, so but the main point here is there's this whole family of solutions that fit the data. Now, I also have some prior assumptions over x. Here, just for sake of argument, I'm going to assume a very simple Gaussian prior over x, which means that I believe that small values of x are more likely. But this is analogous to the natural image statistics prior, but here we're just using simple Gaussian. Now, by Bayes' rule, that is just the laws of probability theory, that tells us that our belief in the unknown values is this. It's this distribution, which is the product of the likelihood and the prior. I'm also assuming that this is a constant, that we have no prior over b, or it's uniform, times some normalization constant, and that gives us this plot. So here, now we don't longer have this whole family which equally fit the data. Since we believe that smaller values of x are more likely, we have a preference for being towards the bottom part of the hyperbola. Now, the obvious thing that a lot of people would do here is map estimation. So what's going to happen if I just do map estimation here? That is where I solve for the most likely value of x and b together. Right, you're going to go all the way off to the right because since you want x to be small and you can pick any point on this curve, you're going to try to make x smaller and smaller and smaller until you have x as 1 over some huge, huge value. And so you're essentially going to go as far off to the right as you're allowed to within the constraints of the problem. And that doesn't seem like a very intuitive solution. Now, if we do sort of a more correct Bayesian thing, and more is a qualifier here. It's not the correct thing. It's more this formula is the right thing to do. Let's just consider the marginal likelihood of B given the measurement y. And here we're essentially integrating out this unknown x. We don't know what x is, and so we actually have to consider the whole distribution of possible values of x, and it looks like this. Now, what this formula says is, if I want to evaluate any possible value of B, what I should do is add up an entire column of this image here. So essentially project all possible values down to here, and then I get this curve. So what this curve tells me is that I actually believe that B is more likely to be 2 than anything else, because the volume on this vertical slice here, that is over all possible values of x, B equals 2 is the most likely, is the best choice. So therefore, because this slice has the most volume, this point here is actually the peak for B. Now, this curve is not very peaked. There's a pretty wide, still a lot of variance in this distribution. But now we're actually getting to a more sensible value for B than we did with a pure map estimate. And if we wanted to, we could do the same thing for x. So the main message here is what you would do is choose the most likely value for B, integrating over x. And if you also want to know x, you also choose the most likely value for x, integrating over B. So if you haven't thought a lot of probability theory before, this might not be perfectly transparent. But hopefully, if you have seen some of it, this gives a different way of thinking about how you can make this choice for x or for B. Now, there's an additional complication, which is in our problem, computing this integral for each pixel in an image or each pixel in the kernel that we want to solve for is hopelessly intractable, so we have to use approximate methods. I won't go into the details of how this works. We use something called variational Bayes, which comes up with an approximating distribution QXB to this posterior we want to compute the max marginals of. So if we look at this hyperbola, the map estimate is way off over here, whereas the variational Bayes estimate is over here. We're essentially fitting a Gaussian to try to find a region in this hyperbola which has locally a lot of volume. And there's a tremendous amount of details in how this works, which I don't want to get into unless there's questions. Just to evaluate the quality of this approximation method, the true marginal, which says B should be 2, it has a preference for being over here, but there's a lot of uncertainty in this distribution. Map is very far from the peak, and variational Bayes basically does the right thing. We'll skip that. So now we have these two things. We have a model of the image, the convolution process. We have a prior for natural images, and also we put a prior on kernels, which is we believe that they're sparse. Most entries are 0. And this, coupled with the variational Bayes inference technique, is what we're going to use. So just formally, we observe an image y. We have an unknown kernel B, unknown sharp image x. We want to describe the posterior distribution over these unknowns. It's the product of a likelihood term, an image prior, and a blur prior. The likelihood term we use is a simple Gaussian noise model, which is just essentially a Gaussian penalty on the difference between, this is basically just a data fitting term, measuring the distance between how well pair B and X fit the data and an image pixel. We fed a mixture of Gaussian's model to the observed image statistics, the observed gradients, and we fed a mixture of exponentials model to some typical blur kernels. And so we get this blue curve, which is just a mixture of exponential distributions, a linear combination of exponentials. And this is chosen just to enforce constraints that the kernel be positive and also sparse. It does not enforce any connectivity on the kernel, so you could have a bunch of dots in isolated places in this kernel, which doesn't make sense, but it's a little bit harder to enforce. So if we just do map estimation, that is, we write down the log probability of the data, which is squared ends up being a squared error term plus these regularization priors, we get this terrible result. It doesn't really look like what we want. The kernel doesn't make sense as being a connected curve. And the image doesn't really look a lot sharper. So when we apply our method, then we're going to get a better result. So the method we're going to apply is we use variational bayes to come up with distributions over the unknown image, the unknown kernel. We compute max marginals to get a kernel. And then we just do a standard deconvolution method, which is in Lucy, to get a better result. I think I haven't done enough experiments, but I think the more recent stuff that Anant and Fredo and so on developed might also work better for this step, although it still has some issues, I believe, from talking to Rob. And I should also say there's a lot of implementation details which I'm going over, because there's a little bit of tricky math involved in doing all the details. But really what's important is the mathematical formulation. So the map estimate is not very good. The variational bayes method, I think, is a lot better. So for example, there's this point off in the distance. I think there's a little bit of trash in the scene, which in the real image got turned into this path. And our method essentially automatically reconstructs that path and sharpens the image a fair amount. So it looks like I'm running a little low on time, so I'm going to skip these experiments. So one thing that's important to know, like I mentioned, we're making a lot of approximations. We're assuming that the process is a linear convolution, and we're assuming that the whole thing is linear, so that we actually are gamma correcting the images before we apply the process. If we don't gamma correct, then it doesn't work. Fortunately, it seems like all of the digital cameras we try use this sRGB format, which mandates gamma is roughly 2.2. Saturation causes problems. I'll show you in a moment. JPEG artifacts mess things up. Other, scene motion when objects are really moving. Any place where our model doesn't fit the data, we're going to see artifacts in the results. Also, our image prior is pretty simplistic. Just really looking at pairs of pixels and gradients between them. And there's many ways to improve that, such as correlation between color channels. So I'm going to show a variety of results of our method. These are all taken from, none of these are our own pictures. These are all pictures from various different people that have provided to us their own Blury pictures in hopes we could help with them. There are, of course, artifacts in them. We're not getting back a perfect de-blurred image, but I believe it's a big improvement over the existing work, and it gets a lot closer to being usable. So here's a city scene. Now here, this is an image with a whole lot of saturation, which we don't model, so I didn't really expect it to work very well. But it actually did a pretty good job of getting out, collapsing a lot of these light sources to points. And the kernel here, the shape of that curve, looks a lot like these shapes. The only thing here, this region is very saturated, so it kind of turns into nuclear radiation. But aside from that, I think it looks pretty good. And you just look in the detail, you can see it's a lot more like a sharp image. Here's another picture that's taken inside a museum, which doesn't allow flash photography. And we get a reasonably linear or continuous kernel and a nice reconstruction. Whereas if we apply the blind deconvolution method in MATLAB, we get it doesn't really help with the blur. And just to compare, you can see that the output here is a lot sharper than the original or the MATLAB approach. Here's another image of someone you may know. One other detail I should mention is that, one of the many details here is that we're actually applying the kernel estimation technique just to a user-selected subset of the image. So here, Rob has basically chosen this region here as being a good candidate for estimating the kernel, although mainly this is an issue of speed and trying to remove outliers such as saturation from consideration. Here's MATLAB's attempt to de-blur, which doesn't de-blur a whole lot. Sharpening doesn't help much. And our method does a little bit better in terms of getting a nice sharp version of the individuals here and a nice continuous kernel out as well. So one way of evaluating this is to look at, in some images you could kind of identify the motion of points that look like the kernel, similar to what I showed before. So in this case, if you look at his eye, you might notice there's a kind of a curved path in his eye. And this path roughly matches the kernel that we got. And after the deconvolution, that kernel has been that path has been collapsed roughly to a point. You can see a lot of color artifacts here because we're not really modeling correlation between color channels. Also, the JPEG compression, I think, messes up the different color channels quite a bit. Here's a blurry image on a subway, and the text and the writing becomes much clearer. Now there's parallax in the scene. This pole is moving relative to the, is much closer to the camera, so it creates some ringing artifacts nearby because the parallax is not modeled by the algorithm. Here's another scene. This one actually has a little bit of motion blur, so we didn't estimate a kernel over there. Here there's actually a nice, smooth, continuous kernel and a much sharper reconstruction. This is the one I showed before. Again, you can kind of see in the blurry image, this kind of path seems to be roughly the shape of the kernel, and we get that out. Again, displaying deconvolution from MATLAB doesn't help much. So here's just a few more examples of looking at the path, trying to identify paths in the image as compared to the kernels that we got. And you can see that quite often they're very close. Now I should emphasize that we're not actually trying to identify these paths because a lot of times there are images which don't have these paths. And when we've attempted to directly look for them, we haven't been very successful. It's not clear how to identify what these paths are, although we as humans are able to find them. Here's an image with a very small amount of blur. This may just be out of focus. When we estimate a very small blur and it sharpens it a little bit. Sharpening basically does the same thing in this case. Another example of this family. Here we can sharpen a little bit. And one thing is now you can actually read much better. It says lizard on his sweater, whereas before it was a lot harder to tell. Here's Rob giving this exact talk at SIGGRAPH. And Paul Debevec was a chair, so he took a picture of it. These people who like photographs. And here you can see that like the text in the AV equipment becomes readable as a result of the deconvolution. Here's a picture taken by a wildlife photographer. So here it's a zoom lens, very hard to keep steady. And the result, nice continuous kernel. There is some noise in it, but it is a nice kernel. And one thing you can see is now the legs of the bird are now visible, whereas here they're not. There's a fairly substantial amount of ringing here, which I think is due to probably due to saturation in this region of the bird, because again, saturation is not really modeled. This image has kind of a double exposure effect, and I was getting this problem all the time in pictures I've taken. I see this it kind of looks like the camera was jolted during the picture, and you might think that the obvious thing is, well, let me ask you. So why do you think that is actually? So why do you see this kind of double exposure in a blurry picture? Sorry?
Pressing the shutter?
Right, so that's what I thought too. You press down the shutter and it kind of jerks the camera. But the thing is, you press the shutter before the shutter is actually open, right? So that can't be the thing. But then you release the shutter, and that can shake the camera if the shutter is still open. And so, personally, when I remember, I actually just try to hold down the shutter longer. But sometimes I forget, and some cameras don't let you do that. Anyways, in this case, the method actually sort of discovers this double exposure kind of kernel and is able to collapse a lot of these double images into one. Again, there's ringing in regions which are saturated. Here's an example that our method doesn't work on. We didn't actually try applying it to this one, but there's motion blur, there's depth of field, there's different objects moving in different ways. So this is one thing we can't handle. Here's just another example of really serious saturation. These paths are different, and so it seems like there's not much hope for our method in its current form from working. But maybe perhaps with a more generalized model that knows about saturation, knows about motion blur, in-plane rotation, might be able to handle such situations. The code for this project is available online. Sign up on the webpage, and Rob will send you a URL for the source code in MATLAB. So just to summarize, I think what we've shown is basically using natural image statistics and a good Bayesian approach is able to solve this problem that otherwise seems under-constrained, and there's been a lot of work on. And it's really the first one in deep learning literature which can handle these really complicated blur kernels. And I think this is reflective of the kinds of problems in vision which I find exciting. that we as humans look at something, it's very obvious for us what's going on in the image, whether an image is right or not. And it's not clear how to pose things mathematically. But with the right priors and right inference techniques, we're actually able to get better results and perhaps say something about what information that we as humans are able to exploit in these problems. There's lots of future work. I mean, we've really just, in a way, created more questions than we've answered. Maybe we can do better deep non-blind deconvolution. It'd be nice to combine this with other sensors. It'd be nice to improve the model to represent other phenomena that we haven't actually handled, saturation being the most important one. And of course to deal with more complex blurs. And there's been some follow-up work, such as what Fredo talked about, which has been addressing some of these issues so far. Okay, I'm going to take questions at the time.
Can you say that usually the kernel is because of the motion of the camera is always a path? I mean, if this is the case, then could you just model this convolution kernel as a curved line and maybe get better reconstruction results? Yeah,
absolutely. So if we can model the kernel as a curved line, then we should get better results. I think it's mainly for numerical issues that make them more tricky. So one issue is we have to allow for curves of being different lengths and having different, like the kernels maybe of different sizes, like the width of the line may vary in different places. And then it's just some mathematical issues in order to use that in the model. But
parameterization to discover how much you dwelled at one point and then moved quickly through another.
Right. So you can represent the fact that it's a space-time curve. So you can represent that, but searching over that space is a little difficult.
Well, it seems like you could do it as a two-stage process because you get such nice kernels in your method, and it makes sense to me that it would be very hard to encode the linear, the path assumption into the method directly, but once you have that initial estimate, maybe you could go and kind of clean up your kernel with these additional assumptions without...
Yeah, sure.
Could you speak a little bit more about the correlation across color channels, how that's a problem or an advantage in your algorithm? Because there's a very heavy-hand correlation that occurs in cameras, which is the white balancing that actually correlates the three color channels in a very strong manner through matrix rotation, possibly, or other techniques. Have you tried out different white balance settings and seen if they're different? Does that change the results of your algorithm?
Well, so we've just been doing the processing in grayscale. In terms of estimating the kernel and deconvolution, just all three color channels separately. So the main thing is that there's really information across color channels that we can use. Similar to what Danny talked about this morning, if you see an edge in one image, in one color channel, it's much more likely you'll see an edge in another color channel. And so these edges can reinforce each other and make me usable better priors, basically.
Something you mentioned actually might be a good topic for discussion of all these computational photography methods is that if you use consumer cameras, I've actually taken a color chart and did some experiments, and what goes on in the conversion from RAW to the JPEG that you actually get when you download it is quite amazing. So they have these nonlinear curves where they boost the midtones and boost the reds more to make it more appealing, and it seems that if you work on consumer images, that all of your nice mathematical frameworks go actually out the window, kind of. So it's great for raw, and then, I'm impressed by the results, but I'm wondering how this processing has effect.
Well, in our case, we're working on the JPEGs that people took with their pictures, and with too much processing, you have a problem. We're basically just doing radiometric calibration to try to invert that transformation process. JPEG artifact. We're not inverting JPEG artifacts, but that's one way to go, is try to invert them. Another way to address them would be to include all that in the model. That'd be a lot more difficult, but conceptually, there's no problem in doing that.
Great. Thanks a lot. So our next talk, as I understand it, is going to be a 3-laptop talk, if I'm not mistaken. So hopefully you will bear with the speaker. speakers. We're going to be hearing from Noah Snavely, who is a graduate student across the lake here at the University of Washington, who's been spending an awful lot of time out here, and Drew Steedly, who is in Live Labs, which is sort of another group, much like Microsoft Research here. And they'll be talking to us about photosynth, which you may have seen in some newer stuff, and other cool stuff I heard. Which are you? Number 2? Yeah. That's okay.
Yep. There we go. All right. Thanks a lot, Michael. So, as Michael mentioned, this is going to be a joint talk with Drew Steedly from Microsoft Live Labs. And what we're going to be talking about are several different projects, including object movies, photosynth, and other cool stuff. So, but I'm going to preface the talk by talking about a different project that I worked on last year with Rick Salisky and Steve Seitz from the University of Washington, which is the phototourism project. And the motivation behind this project is something that's kind of been somewhat of a theme at the Symposium. There's just so much data out there on the internet, so much imagery. There's billions of photos available online. It's just a vast collection of digital imagery. So, for instance, if we go to Flickr and search for photos of London, we get almost 3 million results. We search for any particular famous object, like the Trevi Fountain, we also get thousands of photos taken by many different people from many different viewpoints, under many different lighting conditions, weather, and so on. So this is a really great, rich source of visual information about our world. But it's organized in a very loose way. So the goal of the phototourism project is to use geometry, use automatic computer vision techniques to reconstruct geometry from these types of image collections, and then use that more structured representation to do more effective browsing of these data sets. So given an input set like this, we reconstruct geometry. For instance, this is the Trevi Fountain. You can see this point cloud representation in the background here, and all these camera frustra, which represent locations where a photograph was taken. And again, this is automatically computed using computer vision techniques, which I won't get into now. But once you have this structure, you can do some kind of powerful things. Like if you want to see a photo of a particular object, like this statue here, you can just select it, and the system will go ahead and find a good photo of it and morph to it, and suggest other possible photos of that object. Here's another phototourism data set of Half Dome in Yosemite. So again, we see the point cloud version of the mountain in the background here, and you can see all these frustra taken, or these photos taken across the valley by all sorts of people on vacation at Yosemite. You can also see photos snaking up the mountain itself, taken down from the valley and up on top of the mountain by someone who's actually climbing the mountain. So this video just demonstrates some other types of things you can do with this type of, once you have this kind of data. If you find a viewpoint you really like, you can easily find other similar viewpoints and view them as a stabilized slideshow, which means that the object itself will be fixed in the viewpoint. But you'll see this beautiful time-lapse kind of image as different photographs cycle through different times, different seasons, and so on. And we've also had some success registering historical imagery, such as this photo from Ansel Adams taken in 1960. So we've tried this on a variety of scenes that we've downloaded from the internet, and it tends to work pretty well. It doesn't always work, but it's fairly robust in our experience. So, here's another type of scene we'd like to handle. And it's somewhat different from the scenes the types of things I've been showing you in phototourism. It really consists of a single dominant object that's really the focal point of the scene. These are images, of course, of the Statue of Liberty taken from Flickr again. So now I'll kind of look at the reconstruction from a top-down view. And you can see that the distribution of photos really reflects something about the scene, which is that there is this very dominant object. There's a pretty dense set of photos taken taken in the water here by people on boats, and another dense cluster taken on land. But they're all pretty much focused in on this one object. It's clearly the most interesting thing in the vicinity. So we've developed another user interface called Unstructured Object Movies that allows you to allows a user to very fluidly and interactively browse scenes like this. So I'll show a video of this. Again, this is work with Steve Seitz and Rick Soliski. Here's some of the input photos, and now when you look at the interface, you can very smoothly, interactively change the viewpoint, and this continuously displays a new photo and warps it to that view. This video is a little bit jerky for some reason. Let's see. You can also zoom in and zoom out, and again, the system automatically selects a photo of the right resolution. Now we move forward. We're standing underneath the statue looking up at it. And again, as we navigate, as we orbit around, the system automatically selects a photo to display. So how does this work? It's actually very simple. So the first thing we do is define a orbit point. In this case, it's the center of the statue, and this is a point about which the user can do things like orbit. In this case, we define the point manually, but you could also imagine finding it automatically. So if this yellow triangle is our virtual view, the system allows you to do things like orbit that view around this focal point. But how do we display a kind of synthetic view at any given virtual viewpoint? Well, we simply select at any given virtual view a photo that the system thinks will best represent that view. So that will be a nearby photo of hopefully the appropriate resolution and field of view of the current virtual viewpoint. So in this case, it might be this photo. So to warp, we can't display it. We can't directly display that photo. It may need to be cropped, rotated, and kind of centered to get it into the right place on the screen. So what we do is we simply project it onto a plane that passes through that orbit point and is orthogonal to the viewing direction of the selected photo. We project it onto that plane, then reproject into the virtual view. So that kind of warps the image enough to get it into a rough alignment with the actual scene. And if you have a dense enough set of photos, again, data is a key here. You tend to get pretty good results that actually give you a strong sense of 3D. So, and this process repeats for any viewpoint that the user selects. Here it might select this image, reproject it into the view. Over here it might select this image, and so on. So here's another example, and again, the video is pretty choppy, but let's see if I can. If I play it in, let's see. It's not much better. Let's see. So well, I'll just play. My laptop is acting really slowly for some reason. But what you'll notice with this scene is that there's a large degree of appearance variation as we move around. And that's because there's daytime photos, nighttime photos, and everything between in this data set. So one thing the user can do to avoid this is to turn on a similarity mode where only transitions between similar photos with similar appearance are selected. So this smooths out the experience somewhat. We can also turn on color compensation, which kind of corrects the photo to better match, corrects the color of a photo to better match the previous photo. And this also tends to smooth things out quite a bit. So in this case, we've also segmented the photos into daytime and nighttime photos semi-automatically. So the user can choose to view a daytime version of the scene or a nighttime version of the scene explicitly. So here they zoom in to the nighttime version of the scene and then switch back to daytime. Okay, here's another example of Stonehenge. And in this case, the jerkiness is partly due to the way we're doing things. So you'll notice it's a little bit more jerky than the previous examples, and that's because this planar imposter we're using is not a very good, doesn't fit the actual geometry of the scene in this case. So you still get a good sense of the structure of the scene, but it's more jerky than if you were to use a better imposter. So this final example, this example shows a handheld object we captured, and when we view it in our viewer, we can kind of interactively select the viewpoint, and kind of it's actually pretty fun to play around with this object once you've reconstructed it and loaded it into the viewer. All right, so here's one final example of the Notre Dame Cathedral. And in this case, what we're doing is we're starting from pretty far away. We're continuously moving forward towards the cathedral. And as we do so, we get higher and higher resolution views. So this is kind of a continuous zoom of several hundred, well, maybe 100 or 1,000 times. So as now we're very close to the facade, we get very high resolution views. So now we move back a bit and orbit around the cathedral. Okay, so I wanted to show one last example. So here's another data set that's pretty interesting that we've applied our system to. So this is the Pantheon, and if you look at the reconstructed camera locations, they're pretty interesting. So in this case, you get both the inside of the Pantheon, and you get a reconstruction of the outside, or at least the front facade. So the reason this works is because there's actually photos taken at the door that can see both the outside and the inside. So you get this very nice reconstruction that includes both interior and exterior views. So one thing that I'm not going to talk about in much detail, but that I've worked on with other collaborators at UW, Ian Simon and Steve Seiss, is kind of clustering these views to find canonical or very representative images of the scene. So this distribution of views is sampled from the internet, and it in some way it's a distribution over views that people think are interesting. So you can imagine that you can use that to figure out what is interesting in the scene. So I'm not going to go into detail on that. I'm just going to show a video which is an adaptation of the object movies interface I was showing with some what we call canonical views highlighted in this bar underneath. And I think the video is, let's see. Let me try that one more time. Okay. Yeah, maybe this video doesn't want to play, so I'll just skip over this. If you're interested, I can show you this. I can show you this afterwards. So now I'm going to switch gears and talk about another project, which is joint work with collaborators at University of Washington, including Brian Curlis and Steve Seiss, and at MSR, Hughes Hoppe, but mainly worked on by Michael Guzela, who is a postdoc at UW, who's going to be a faculty member at Darmstadt in the fall. So the goal of this project is to go from these very sparse geometry representations that I've been showing you, these kind of sparse point clouds, to actually dense 3D surfaces, such as this example of the facade of the Notre Dame Cathedral. So we want to do that fully automatically, again from these images that we find on the internet. This problem has been looked at extensively, usually using techniques known as multi-view stereo, but usually with images that are captured using very controlled setups, with controlled lighting in a laboratory situation. So the main difference here is that we're working with very uncontrolled imagery, images that you just happen to find on the internet that were taken by many different people under many different lighting conditions. So that poses some challenges. So if you just look at a bunch of these images, you can see some of the types of variability that we have to deal with. In this case, these are 206 images taken from Flickr from 92 different people. And if you look at a few of them, you can really see the differences. So there's huge variation in scale. This image was taken from quite far away. This image was has a lot of detail. There's differences in viewpoint and lighting. There's also quite a bit of occlusion. In this case, a person is filling up a lot of the view. So these are the kinds of things that we need to be able to deal with in the algorithm. And I'm not going to just explain it in any detail, just to say that the approach is to first compute a depth map for each image and then merge these depth maps into a global 3D model. So there's some details about how we compute the depth maps. Basically, we want to have a good set of neighboring views to match with. But without going into detail, having a lot of data, again, helps this problem a lot because you're bound to find good views to match with. In this case, views that are of similar or higher resolution and that are kind of have a good sampling of baselines. And we use a window-based matching algorithm, which I won't talk about right now. So let me switch over to the other laptop. Okay. So here's an example of the type of result we get. And this is actually a zoom in of the front portal here, and you can actually see that there's quite a bit of detail in the above the portal. You can see these figures in pretty significant resolution. That's because there tends to be very high resolution views of these of this part of the cathedral. Okay, so I think I'm running a little bit low on time, so I'll just quickly go through these other results. This is a reconstruction of the Venus de Milo from 129 images on Flickr. Here's images of a cathedral in Pisa, again taken from Flickr, and here's the model we get. So it looks pretty good, but how do we actually measure how well we're doing? Well, in this case, we're lucky enough to have a laser scan of the same part of the building. So we have ground truth with which we can measure accuracy. And it turns out that compared to this laser scan model, 90% of the points lie within 0.128 meters of ground truth, which maybe 5 or 6 inches, somewhere around that, for a building that's 51 meters high. So actually, we're getting surprisingly accurate results. And again, I'll just briefly show a model of this one. You can see quite a bit of detail, such as these ridges in the roof here. All right, so now I'm going to switch over and have Drew talk about photosynth. Okay. Yeah, sure.
So I presume there are much more than 200 pictures of the Notre Dame.
Mm-hmm.
Why did you just use 200?
Well, so there's a few reasons for that. I think the biggest one is right now the structure motion part of it is not that scalable. So you're right. There's probably many thousands of images of the Notre Dame Cathedral, but right now the structure motion, which is the front end to this multi-view stereo procedure, it doesn't handle that number of images.
But it might be that you can do structure for motion on a smaller set and then just add the rest, right? You don't have to
right.
do it in one shot.
Right. Actually, in some cases, we've been doing that, and I think that will allow us to work with a lot.
I feel like if you add all of them, it will actually make things simpler, right? All the other things.
Mm-hmm. I completely agree. Yeah. The more images you have, it will never hurt you. It'll only make things better. Not positive. Let's try this.
One more time.
This is A, so this should be PC2.
Yeah.
Both screens. So this should be the right one.
Take 24 by 760.
Yeah. Is this not? Yeah.
Another one over there.
So it's not responding to the mirror. Yeah, I'm doing that right now. It's not responding to that.
We'll try the other cable.
Yeah. Okay. So the disconcerting thing is that it's not doing it. Let me try. Try to get it to rethink about it. Should I reboot here, maybe? Let me log off. Try that again. Go ahead.
Are there any more questions?
Let's see, do we have any more questions for the previous speaker?
Yes, Frank.
Frank?
But you showed these models, they didn't seem to be depth maps. They seem to be like 3D models. How do you get these depth maps into a 3D model?
Right. So I didn't talk about that in any detail. I was showing the merged result. So once we get the depth maps, we use typically the Poisson mesh generation method that Hughes Hoppe worked on to get the final depth map. So we have all these depth samples, and Brian might be able to elaborate on this more, but each depth map gives us a certain set of depth samples. We also get normals, so we basically want to come up with a consistent a mesh that agrees with all those samples.
I see.
Any other questions?
You want to do Stonehenge better?
How would you do that? To get the other kind of prior or the cylinders?
Right. So I actually did try a cylinder, and it doesn't really work any better. In fact, in some ways, it's worse.
How about a couple of surfaces? You could do a cylinder and do some sort of graph cut to decide whether it should be on the front or on the back.
Yeah. Well, so far the system works interactively, so I'm not sure how much more machinery you can add, but I think something like that might work pretty well. Or you could just feed these to Michael Guzela's multi-view stereo code and get.
It would be interesting to know what is the kind of compromise between a plain cluster and a full 3D model. It would be nice to have something in between, like a layer-based representation.
I agree. There's something very appealing about planar models in that people are very used to seeing planar distortions, and the artifacts you get with them aren't quite as objectionable as artifacts you get with, for instance, texture mapping a person onto a arbitrary object. But yeah, I agree. It would be very interesting to try and find some compromise. Yeah.
Okay.
Is this on? It's turned on. Can you hear me? This is showing going through? Okay. All right. So when we, so I'm in Live Labs, so which is another research lab here in Microsoft. It's more product driven than MSR, and we saw Photosynth or phototourism, which was a collaboration between Rick and Noah, and we said, this is great. We should do something with this, and so we about 6 months after we started working on this, we released a tech preview, which is mostly based on phototourism, and it's also got a component. So I wrote the 3D reconstruction side of things, and a local company that was based in Seattle called Sea Dragon was purchased by Live Labs as well, and they have a nice technique for zooming into high-resolution images and streaming that over the web very smoothly. So this past fall we released 4 collections that were built. This St. Peter's, a lake up in the Canadian Rockies called Grossi Lakes, a pair of them, and then San Marco, which is in Venice, and also a local artist's gallery. So this is a few hundred photos of his gallery, and you can see the point cloud similar to what Noah was producing. And here you can see all of the original photos. So this is actually streaming live over the web, so you can see part of the Sea Dragon technology where it very smoothly fades in data as it's being streamed over the web. So if you go back to the 3D view, you can also see these arrows on the left, right, up, and down. So these allow you to find images that are to the left of where you're at now. And then you can go back around to the right. You can also zoom in and out with these and jump to different images. And then the scroll wheel allows you to zoom in and out of these photos. And so one of the things that was needed to take Noah's work and make it into a product that's streamable over the web is this technology, because a lot of these images are several megapixels. And actually these paintings were scanned at very high resolution, so these are tens of megapixels. And when you have that much detail, you can do things like zoom in. So here is let me go to the right here. There's a painting over here that I particularly like. Up here, where you can zoom in and see brush strokes, and you can see even the pattern of the canvas underneath. So the other thing that you can see here is the point cloud. So I'm not a very good video game player, but you can navigate around and actually see the 3D structure of it. So then after we released this, there was a lot of interest in this, and one of the partners that we had was MS in Asia, and so they wanted to put together something where users could actually contribute their own photos to it. So the lawyers here would not allow us to go scrape thousands of photos off of Flickr and then repurpose them for Photosynth. So the first 4 collections were just photos that we had had people take internally. But with MS in Asia's help, we were able to create an initial photosynth to get people interested in it, and then they had a promotion where they asked people to take photos and submit them to us, and then we added them in, and so you can start to see some of the user photos here, and they add a lot more character to the photosynths, make it a lot more interesting. And so this is also on the web now, and you can go see this live. Again, because all of these photos are here, this abundance of data, you can start zooming in and see a lot of detail in this palace just from all these different photos. And again, you can see the point cloud that was reconstructed here and this fly around. And also you can see where all the photos were taken from. So you do that by just turning on this little photo, the camera button, and then you can see all these little orange pyramids are where the cameras were taken, the images were taken from. And you can see a lot of people were kind of centered around this front entrance here. And so then we also had one more set of collections. So the BBC is currently doing a 6-part series about how we built Britain. And so they, similar to what we did with MS in Asia, they went and took a bunch of photos of a place, Ely Cathedral. Let's actually go back. And Ely Cathedral, the Burley House, Scottish Parliament, and Trafalgar Square, and a couple other places. And we built these initial collections, and they aired these on their TV show and put links to these. And this generated interest, and they also collected photos as well. Let's see. And so then we additionally added these photos into the SIMP. So you can see some of the photos that they had. Here is actually the bus. They sent a bus out to collect the photos. And then they sent those to us and put them in. And so again, you can see that there's just tons of photos here. And we actually had so many photos that we had to prune some of them out just to make the synth not be overwhelmed with images. So it's really nice to have that much data. And again, you can see the entire structure reconstructed. And where all the photos were. So they're just all around here, and you can see there's a large density of photos here, the different focal lengths and positions. And again, this was the reconstruction was done completely automatically here. So one that I find particularly interesting is this Burley House collection. Because there's not that interesting apparently. All right, we won't be showing that one. How about Blackpool? So Blackpool Tower is they have a British variant of like Dancing with the Stars that's held in this ballroom, and there are tons of photos in here, and so it's very compelling to be able to browse around and navigate here and see the people dancing and moving around in here. And again, we've added user photos to this too, so this is also on the web, and you can go browse around and see this live. You just have to download and install the ActiveX component. And again, there's just tons of photos that were put into the synth, and you can see them all here. And let's see, here are the dancers. Okay. So we're currently working on this, and we're actively working on something where people will be allowed to build their own photosynths and also where contribute their own data and put this on the web. And so we're actively working on this, and we hope to have a release here soon where people can play with this and build their own collections. Okay.
You ran a little bit late, but there's one question to do with Judy.
You mentioned a couple times that there's a limit in the number of photographs that you can handle. What is the limit, and is it a C-Dragon issue or a photosynth or a UI?
So there are a number of limits. So the reconstruction is kind of a slow process. So we're actively working on making that faster, and we've made substantial improvements to that. There's also an issue of viewing these things, right? So if you have thousands of photos, picking out the one that's interesting is tough. And so, it's hard for an automatic algorithm to know what the what a good photo is, what a compelling photo is. So you could imagine something like a dig type interface where people vote up and down, and we could use users to help prune these things out or percolate the best photos to the top.
Okay, with that, I want to turn the floor over to Rick Zielinski, who has some closing thoughts for us, and let him take it from here.
Yes.
Let's see. This could work. There we are. Okay. So I hope, let me just get Mike up here. I hope that everyone's enjoyed their day here. Thank you all for coming out, and especially thank you to our external speakers who agreed to stay an extra day after the faculty summit. And also I'm really happy to see all people from research and product groups who decided to spend some of their valuable time with us. I don't actually have any specific thoughts. I thought I would use this time to have a general discussion. So in the absence, if other people, if people don't have specific thoughts, I put together a few general 4 sort of areas where we could talk about, and they're summarized here, and I have a few more detailed slides to lead the conversation in each of these. But let me just first open up the floor. Are there any sort of high-level questions that people would like to discuss at this point before I kick off some particular topics? Any questions that have sort of been piling up throughout the day? Things like that? Nope? Okay, well then I'll just sort of jump to the first one, and I'll ask a few questions. So I was collecting some quotes I really liked today from various speakers, and I think Fredo at one point said, computation is the new optics. So one of the questions in my mind is there's a lot of theory about things we could do, but there's some debate about whether this is actually percolating down into the hardware that's coming out. For example, Sri Nayar showed some beautiful results with doing, changing the Bayer pattern to something to let you do higher dynamic range. As far as I know right now, Fuji is the only person who's selling a higher dynamic range camera, right? But we are seeing double lens cameras which have a wide angle and a narrow angle lens. And there's also this digital lens, which some of you know as the planoptic sensor from when Ren Eng was at Stanford. So I was just looking for his webpage and found that indeed he's already got a startup company doing this. And there's an interesting little quote here that maybe will make all the stuff that Aaron and Fredo are doing obsolete, right? Because with this camera, you never get blur anymore. So, I think some of us have seen this technology and may have some questions about whether it's the right way to use pixels. But there obviously is some movement. It's going to be interesting to see whether these novel hardware sensors actually make it out to the market. In other words, when will some of this technology start to displace what we see, for example, in the high-end cameras? When is the Canon or the Nikon latest model going to be willing to give up some of their pixel resolution to get higher dynamic range? So do people have any thoughts on these questions, observations?
Okay, so I guess on that,
Robert.
I just did a poll the last couple of days because we're getting ready to do a pretty big...
And can you just speak up, because we don't have... maybe I'll ask if anyone in the back has a portable mic to bring one out, but for now, just speak loudly. Thanks.
Okay, so I queried in the last 2 days all of the major camera companies relative to high dynamic range. This has to do with the press release we have coming out with an announcement related to HD photo and standardization. So in that, we found different, like some of them clearly by defensive response, basically are doing something but don't want to announce it yet. And so there's some tendency not to signal other companies to engage in. We've also talked to companies like Foveon, who are going to make an announcement in our press release, not necessarily doing high dynamic range yet, but have concepts that are close to it. We did find many companies building high dynamic range sensors for automotive vision systems right now that are now going to move into cell phone and digital still camera sensors. Okay, so that seems to be where the innovation was financed.
I see.
High dynamic range was for automotive sensors. So there's a company called OmniVision, for instance, and they have it for automotive and they have it for security cameras.
Right.
Okay? And then they're moving into this. There's a lot of interest in this, though, right now. And so one of the key things, for instance, that Federico Fagan told us from Bowie, for those of you who don't know him, he invented the microprocessor at Intel. He said a lot of this was the fact that the rest of the chain wasn't connected, like a compression technology that was convenient for people to use. So then you had a far more limited market segment for the technology. So we feel that through the standardization of the technology that we have with HD Photo, that we may unlock some of the vendors to engage more aggressively.
So the processing chain obviously includes the compression, the display, the representation, the sort of base level software inside operating systems that'll handle the higher dynamic range stuff, right? Does anyone in this audience know about publicly announced work in HDR displays beyond? I mean, some of us know about Brightside, which was the company in Vancouver that was just acquired by Dolby.
We're doing the same thing on displays.
I see. So there is, we should look forward to some interesting announcements in the display space.
So we know, for instance, one company that's going to build us a monitor because they have the pieces in place already. So they're going to build us a monitor for our video and image testing right now related to HDR. The kinds of things that have been a mismatch is some people have done high bit depth but haven't done wide gamut, or they have both, not the contrast, not contrast type of thing. So the objective has been to get all of those things lined up, and we're, like for instance, one company said they have all the parts to do that. They'll make us a monitor, to start with. And of course, Brightside, who's bought by Dolby, and Dolby just announced. So for our meeting in Kobe, Japan, in November, I believe Dolby is going to let us use a new monitor that in the past they've had ultra high contrast. I think it's 30,000 to 1. But they didn't have the wide gamut. Okay, and they have the high bit depth. They have 16 bit per channel. So anyhow, they're going to bring a new monitor for us to display our technology.
But I think from a research perspective, and part of the audience here is research, that's an interesting question because we've only had point examples in the high dynamic range displays. So we haven't really had the luxury to examine what, the gamut gives you the color brightness, right? You're talking about color gamut, basically, which is important to high-end photo professionals, people who care about pre-press, right? The high dynamic range might be important to get that sense of depth that you get with 35 millimeter slides, whereas the high bit accuracy may be important to radiologists who need to see fractures, right? That kind of thing.
But also, you could get banding, right? You could get banding if you don't have the high bit depth.
High bit depth, right? That's right. Yeah.
Because you're expanding the color space, right? So you could end up with graduations.
Okay. Any other comments related to that? Other things people have heard? Brad?
Well, actually, one of the questions I've been around is it seems like we're still making cameras, the lenses and the optics for film. And why can't we start just making the optics to give us what we want? So who cares about distortion if we can correct it accurately? Or the example of, let's make our apertures be something interesting that actually provides us more information. The greatest example is just brilliant. So it's, I think we might be able to make cheaper, lighter, sharper, brighter optics, and knowing that we can do the calibrations computationally.
That innovation probably will happen in cell phones, right?
Right.
You already have mechanical limitations on what you can do with the optics already, right? So there's an incentive then to innovate and to take non-natural captures of the.
Sure. So there are some things that, from my experience, are relatively easy to fix, like radial distortion and maybe even chromatic aberration. If you sort of believe the simple story that chromatic aberration is just warping each color band separately, right? Which isn't exactly.
Like depth, right?
But depth of focus, it's harder to say whether we can actually do things like a blurry image. Ultimately, you've lost some high resolution detail that we can't in theory invert, although if you believe Alyosha, somewhere out there in the world is a patch of the world which has that high resolution that you can hallucinate, right? So that's really interesting. I mean, it's a shame Bill Freeman isn't here because he's previewed some of his work on sort of assorted pixels. And are you familiar with that work, Fredo, or were you involved in that? Where you sort of say, if I can associate my pixels with lenses and taking different kinds of pixel combinations, what gives me a good thing?
Yeah, I'm a co-author on it.
Do you want to come up to the mic and say something about that?
Well, it's related to the fact that now there's more and more work on those crazy cameras, and I've got my coded aperture, Ramesh has his coded aperture, Ren has his panoptic camera, and maybe you've got your stereo camera. Well, the question is, how do we understand how they relate? Which one's better for what? And so we've worked on a theoretical framework to put all of them in the same context and to see each sensor as just a dot product between the light field of the world and your sensor response function, and also to take into account the fact that now we have those natural image prior and that they're changing the rules of the game, recording information about the world, and try to say which one is better for a given budget. Turns out that stereo is a pretty good strategy.
Right.
It might be a reason why we have two eyes. It's even better to do coded aperture stereo. It's two different codes. So yeah, I think that's one of the things that we need is to better model all those things, to include issues about noise, sensor, etc., in order to get a better sense which strategy.
Alyosha?
I have a question for Fredo, actually.
Did I get entrapped?
This coded aperture is such a cool idea, and it seems so simple. Why hasn't evolution figured this one out? Is it because, or has it? I don't know. Maybe are there examples?
There are interesting examples that are related to that. You've got frogs and animals like that have a weird pupil that has kind of a heart shape, and it is believed that. So the code that we're using is symmetric. So you get the same blur if it's in front or behind the plane of focus, and if it's not symmetrical, then you can distinguish between in front and behind. And so there seems to be animals that have pupils that shape, and we might do some of that. I mean, the question is, can you do the inversion, right? So all those techniques are based on, optics that codes the information and then algorithm that decodes it. Is it trivial to do a line deconvolution with those kind of weird patterns in some neural circuit?
It is, because basically wouldn't just the wiring grow to do the right thing? I mean, most of these inversion algorithms are reweighted least squares, right? So you're sort of basically doing repeated convolution. And
the question is, can you do that easily biologically?
I think that's the simple model of the visual system is repeated convolution with nonlinearities, right?
Yeah. The question is, how much boost do you get over, say, stereo? If you already have two eyes, how much is it?
It's a little better, especially to get deeper depth range. Because then with stereo, you've got all the issues of depth of field, which are usually ignored, right? If you use a pinhole model, you're ignoring the amount of light that you're recording, and then stereo is great. But if you want to gather more light, then you need a lens, and then you have depth of field issues.
So is the coded stuff, can it do, so the problem with stereo is that it works really well for something you hold in your hand. So can you do something, is the range better for the coded?
You get similar issues because pretty much your code is doing more stereo, right?
I mean, my intuition says that it's always been a question of the larger the baseline, the larger the working distance, and this coded aperture is a smaller baseline than the interocular distance, right?
Still very small.
To that point, the eye does do stochastic motions or a certain motion path, so in a way it knows its deconvolution kernel, right? I mean, probably because it always doesn't move in a particular pattern, but I guess your eye knows that, and if you actually project your eye and hold it still, your depth perception will increase automatically. It doesn't move anymore. So it's not aperture that's changed, but it's the eye's movement that's steering.
I hadn't heard of that. Just curiously, how many people here are familiar with Ren Eng's work that he did at Stanford? Okay. Now, of those people, I want to see part of you put up your hand one way and the other way. How many people think this will be commercially successful, that it's actually worthwhile trading off pixels to get little lenses and be able to refocus depth?
think that those are two separate questions.
Okay.
I think there's
Oh, okay.
usefulness to it, but
Right.
it's commercial success from
That's true. Okay, so maybe that wasn't fair.
So the problem you have in the digital still camera world is, they appeal to very simple things that people make value judgments on.
Uh-huh.
And now they've run out of steam, and this is a big problem because megapixels per dollar is not yielding incremental value.
Right.
And so now there's cost competitiveness, and you'll see that we're in the first down cycle in digital still cameras in terms of growth and profitability and revenue. Okay, it takes the industry a little while, and this is like a singularity, or it's a point where they have to do some kind of transition, very similar to Intel really making this big thing about gigahertz. Several years ago, and then having to say, we have to pitch some new value to people and change it. So that's, we think this high dynamic range is going to be the thing that causes a change where we explain the value of what this means, including things like the longevity of your photos, right? I take a photo today, and 20 years from now I view it. Will it take advantage of the monitor?
Right.
That you have at that time.
Yep.
People know this.
Right. Yep.
So anyhow, it's going to be a matter of re-educating the value of the market.
Right.
Hovian, for instance, said they have that problem, right? Because they have additional technology in their sensor, but it came at the cost of megapixels. Right?
Exactly.
Yes. Right.
Yep.
So they because people place a lot of value on that instead of the sharp edges and things that are fantastic about their sensor.
Yeah, so that may just be a question of time frame, that eventually, when you stop having progress or you've reached the limits of usefulness in terms of megapixels, then, the other technologies like this, refocusing, right? So, people who I know are enthusiastic photographers like Brad, for example, or Fredo, who spends a lot of time doing photography and inside Photoshop, would you like having the ability to refocus, or do you find that you're always, when you're in the field, you do the right thing?
Sure.
Yeah?
If I get it for free,
Yeah.
No, I think the technological model is very compelling. It does make sense that 10 years from now, we'll probably have the sensor resolution and the processing power to do what Brad is advocating. I think the transition to make that a successful commercial venture is interesting, because the entry point in the photography market is so high, especially the high end. We need more than just a camera, just a sensor. We need the whole ecosystem.
Yep.
I think that's what Foveon has found out. That's what Sigma and Fuji have found out, that a lot of those companies had a one-trick pony camera, usually the sensor, and they didn't have all the things around it, and they haven't been as successful as that. Same thing, Foveon had great resolution, but we had crappy dynamic range.
Irfan?
So I want to change the direction a little bit, if it's okay with you.
Sure.
So one of the questions we have to start thinking about now is who is all this photography stuff for? So us are professionals. We will spend the money. I love the technology behind the Foveon sensor. I wish it was out there, but that kind of stuff. But at the same time, to a certain extent, and I've gotten into this data-driven stuff also. And the question comes up is, if there are photographs out there on Flickr, I take a bad picture and I just find somebody's better picture and I replace it. I don't have to start taking pictures. Is that where we're going? So let me get to the meta level. The meta level question, I was talking to somebody who's a kind of a photography historian. And he asked this question, and he said there is a difference between an image and a photograph. If you start thinking about it, first when I heard it, I was like, what the hell does that mean? But if you think about it, photograph is something about, trying to tell a story and all that kind of stuff. You take it to capture the moment, that kind of stuff. An image could be a lot of manipulations. Could be a lot of different things too, but it could just be a photograph as is. There could be a one-to-one method.
Wait. So
from a natural synthetic standpoint, if you're saying, right?
Yeah.
Right, so it could involve a lot of alterations and different types of things. That's true.
So within that context, asking the question, I could take a lot of pictures into Photoshop.
Right.
And I could change them around.
Right.
I could take 4 different photographs and generate one image.
Sure, and that's the way the world is going.
Traditionally, Ansel Adams dodged and burned all over his photos, right?
Right.
Yeah, absolutely.
No, so that's right. There is this question, and the interesting thing is that in the old days, it was exposure adjustment, and that's been so well accepted by the community that you never questioned the veracity of a photographic evidence if there had been some exposure adjustment, right? But now when you cut something out and you put that on the cover of the LA Times, right, then that's not considered to be a photograph. So there is this whole question, and I think what's interesting is that the technology is making this easier and easier, right? But, I think this is a slide borrowed from Michael Cohen's talk here, and I think it really, the way I like to think about it, I mean, we all know we can do it, but the question is it better for a lot of us if we sort of capture the essence of the moment? I mean, the first thing they teach you in art school is don't try to paint exactly what's there. I mean, you have to train your eyes so you sort of go through those exercises, but eventually you learn to drop the stuff that makes the painting bad, right? You're supposed to rearrange things, do the focus and whatever. So is that the way that photography is heading, from this acceptance that you try to capture reality to something where you're just trying to create something that, of course, doesn't lose the realism, but is what you were trying to say. So, Alyosha?
Well, I think the thing is that humans also don't capture reality. We don't take photographs. We have saccades, we have attention. We are, in fact, more, I think, taking paintings rather than photographs, because it's basically kind of a mosaic of different expressions from different. So in fact, I think this Michael's example is, I think, closer to what humans perceive, and so it maybe not. It's not such a huge divide. In fact, it was never a huge line separating the true photographs and something like a painting. It's a continuum, and I think it's going to stay that way.
Right. So I think, again, I borrowed a couple of slides from Michael, but this one here, the idea, well, let me just back up to this. The idea would be if the camera could, Michael's proposed this before, if you had sort of a rolling buffer inside the camera that was taking continuous high-resolution high frame rate video, then you could create a photograph from that after the fact using this computational optics, as Fredo calls it, right? And one of the things you could do, I mean, you can do high dynamic range because you basically just average a lot of pixels in the dark areas and just take one image in the right areas. You can try to capture the right period of time when you've got the smile on the right and the person's visible on the left. Or you could do something like, if the person's blinking, then you just roll back the shutter, right? So this whole thing we have right now about when you click the shutter is the photograph, and there's a lot of pride among action photographers for knowing when to click the shutter, right? May just be an artifact of the film age, right? And then you're going to basically the artistry in taking the photograph is getting it pointed more or less in the right place, so after the fact you can go in and take the virtual photo that you wanted, right? I have to leave in about 10 minutes, so let me jump to another topic just because I wanted to see a particular debate here between these two camps. And in particular, we have things where you can manipulate images like what Donnie showed, where you just look at the image as a signal, right? There are constant regions, there are edges, and so when you say I want to touch up these pixels, it looks at where the edges are and kind of just manipulates it. Whereas there are other people, Alyosha didn't talk as much about his segmentation-based work, but the idea is you try to have coherent segments and you manipulate those. And there's, for example, grab cut is a technique which again just uses pure statistics about color and edges, and object cut is one where you actually try to do some recognition. So to put them on the spot, I'd like Alyosha and someone else, maybe Donnie, to say a few words about whether semantics is needed or beneficial or premature in photo manipulation. So let's see.
Well, one point in favor of the continuity approach is that sometimes the type of manipulations that you're making, really you want to apply them to regions where there is a smooth transition. Actually, when we were working on this tone mapping project, right? One of the scenarios we were considering was the scenario where you have this sunset scene and you have the sky that's very bright around the sun, right, and its brightness is slowly decaying towards the, say in a wide angle image, towards the sides. And we were saying, well, no amount of segmentation, no segmentation, no hard segmentation or recognition really will help us here. We really want a smooth change in the way we manipulate or what we do to the image in that area.
Right.
And the type of approach that I described earlier, it gives you that, because I mean, it can not only do different things at regions that are separated by strong edges, but it also interpolates things nicely and smoothly in smooth regions.
Right. And your example with the artificial blur was the same, right? You painted the blur at 3 different regions in the image, but you'd like the blur to be sort of smoothly interpolated backwards, right?
Right.
So I guess when there is a continuous quantity underlying things like depth in that, then a pure segmentation-based approach will have trouble.
Right. So, but I'm saying it depends a lot on the application. I mean, in this type of applications, we're really interested in reconstructing some kind of a smooth parameter change across the image. In many other tasks, you don't want it to be, you don't need it to be smooth. And then it's really helpful to just say, oh, this is the sky, I want to do this.
Right.
And this is this is a person, I want to do that.
Right. Alyosha?
Well, so I think the bigger question is computer vision, computer graphics, is it a subjective thing or an objective thing? And I strongly believe it is subjective. We want to recognize things that are interesting to us, humans. We don't want to recognize, some dust on the chair or differances between the skin tones or something like that. We want to recognize the stuff that we care about, people, tanks, and all the other stuff that people are interested in knowing. And the same thing for graphics. We want to synthesize not the physical world. We don't need to synthesize the light field. We need to synthesize the part that will let other people enjoy it and believe it. The question is then how to do it. I think there are 3 different levels. There is, of course, the low-level stuff, which is essentially kind of image processing tricks, which is very important and has gone. We have made huge progress. Then there is the mid-level stuff, which is kind of like the Gestalt rules. We prefer continuity, we prefer close contours, and there has been some stuff on that with the guided fill-in or some recent work with kind of using segments for non-photometric, non-photorealistic synthesis, where it's kind of not on the pixel level, but on the level of regions. I wouldn't call them segments; they could be soft, but on the level of regions. And that, I think, that area really has not been explored enough. All this Gestalt work from the 30s, I think, really we can learn a lot from that, because that's still work that's the Gestalt cues are really cues that are still hard-coded somehow in us. And then, of course, the high-level reasoning, the semantics, and there you have to have some kind of understanding if you want to do things on an automatic level. So Dani gets away with having someone just have these little small semantic hints. And so that's if you're willing to have an interactive application, that's perfectly fine. You have little high-level semantic hints, and then the low level and the mid level kicks in and kind of smooths the rest. But if you want to do something completely automatically, for example, for a whole movie, you need to do something automatic. Then I believe you have to basically hit the hard recognition problem. But maybe it wouldn't be so hard if you have lots of data. Maybe you can do it.
Yeah, and the lots of data comes both in terms of what's out there in the web as that sort of database, and then what's in the sensor, right? If you take more stuff, more resolution, more dynamic range, and so on. Let me just put up sort of one last slide, and maybe we'll try to wrap up in the next 5 minutes or so. I would be interested if anyone would want to venture an answer to the first question, which is, what is the prospect for being able to get a program to make your pictures better, right? I mean, obviously if you have a picture, sometimes it's unsalvageable, but if you have a good photographer, he could take that photo and make it better, right? I mean, that's what photographers do. They take a picture in the studio and then they make it better before they sell it to you. So what are the prospects for computers being able to do that? We know that in some fields like Computer music, I would say it doesn't work that well, right? I mean, for that kind of music it works, but otherwise we don't have it. So is the aesthetics inside making good pictures so AI complete that it's hopeless, or are there some simple rules that we just need a bit of work on?
Well, using Alyosha's technique, we can just point the camera to the scene, and the camera will select the closest picture by a good photographer.
Right.
So it's integer photography. It's, just give the index.
Oliver?
There are some cases, I guess, you can find out what is a good viewing angle to an object, for example. Yeah? What is interesting, there are some things you can compute, so probably this is a solution that the camera suggests a little bit what could be a good viewpoint to an object, just from the shape of the object. But of course, there are many other cases where it's not so simple.
I mean, I'll say one thing, which is, and we'll take Robert and Bob and Bill in a second, is the cameras already have some of this built in. Like when they have the knob that says, are you doing portrait or sports, right? Yeah. They will set the aperture wide on the portrait photographs to make sure you have that fuzzy background, which is something that, one of the first things you learn. But so cameras are doing a bit of that, and they're doing some face recognition and things. So we're moving in that direction. You were Bill?
A couple ideas that I thought of today were, of course, based on the conversation that I had with you. We're looking for scenarios where you can super resolve or enhance through some network service or some type of automated non-human intervention-based approach. One thing that's kind of interesting that we've been talking about is if you have geospatial coding of images that were taken in the same area, and you could find, let's say for instance, I was in Lausanne, Switzerland a couple weeks ago, and I took a bunch of pictures with a really dodgy cell phone camera. And what if somebody else in the same area had a Hasselblad and they had taken pictures, okay? So then you think like, okay, some people have mentioned, well, why don't I just trade the picture I took with a Hasselblad picture? But could we go deeper, and could we look at the texture differences between the low resolution, poor quality image and the high quality one? Keep the naturalness of the snapshot that was taken in the cell phone camera, but refine it with texture information that's in the other photograph, okay, and lighting information and things like this. To me, that seems like something to look into, okay? Secondly, if the Hasselblad picture was part of some clustering where we have identified good photographs, right? A similar type of thing could be done where you begin to understand certain characteristics about the image.
Right.
Or relate those perhaps to psychological cues or different types of things that people find appealing, okay?
Right.
And then attempt to, so for instance, for guiding localized tone mapping, okay? That could be used as a guide to say, really what people like is for these things not to be the case, okay? And these other things to be the case, okay? And that could guide then local refinement strategies in certain areas of the image along with reference image, okay? So I don't know.
So are people in the audience here, in the graphics community, aware of studies that try to formalize certain rules about good composition or exposure, things like that?
There's a whole little conference on computational aesthetics.
Oh, that's right.
It's gone on a couple of times. I haven't attended. I don't know. Did you go to that one in Spain, Manish?
Sure.
They have the Dactyl seminar.
Oh yeah, the Dactyl one, which I didn't end up going to.
There is a SIGGRAPH paper or two, or there's a CVPR paper or two about kind of learning from given a training set of good photos and bad photos.
That's right.
Trying to learn.
There is, yeah.
But it's very simple kind of hacky things that.
Okay.
We tried to learn good cropping automatically, like to do an auto cropper, and no matter how hard we tried, in general, we always tied with just taking the middle 75% of an image. Really good user studies.
Okay, Bill, I'm going to let Bill have the last question, and then I actually have to leave, but you're all welcome to stay here until 5 o'clock to continue the discussion. So.
Well, to your point about, can we help amateurs take a professional photo? I think there's a couple aspects to that. First is probably 90% of taking a good photo is in taking the photo, not fixing it afterwards. So everything from framing to lighting and how we choose to set the camera controls that. there's not much we can do, but there is some. You go back, and maybe not everyone remembers this. Rick and I are old enough, we remember this type of stuff. When people shot pictures all the time on film, and Kodak, the leader in that time, advertised their Kodak Max film, and the TV commercials basically said it's the do-all film. Bright light, low light, indoors, outdoors, motion, stills, action. One film does everything. Well, clearly one film isn't color balanced for every lighting situation or the right speed. Basically what Kodak's marketing message is we've created a fine-grained, wide dynamic range, linear curved film that captures a tremendously wide exposure latitude, a high dynamic range film. Go shoot a crappy picture. It's okay. Out of all that information, we'll make a good print out of it. And that's one of the most powerful features of high dynamic range, is not that we need bright, super bright high dynamic range monitors or all types of stuff. It's to allow us to capture the most possible information, which gives you the fuel to do all of this computational processing after the fact. We have more meat to work with, more things to hold on to. The other aspect of it, in talking about comparing the old adage of what separates a professional photographer from an amateur photographer, is an amateur shows you all their pictures. And so just that opportunity to let amateurs shoot tons and tons of pictures, but perhaps help them cull that in a much more automatic way after the fact. A lot of times, you go out and it's digital, and I shoot all these pictures and I come back with 500 pictures, and I just don't have the energy to sort through them and look through them. But approaches where we encourage people to do that, because megabytes are cheap. We got 4 gigabyte cards and all this kind of stuff. Shoot a ton of pictures and then sit down and have software say, out of your 500 pictures, here's 20 that you probably want to look at. And if you want to dive deep, go ahead. But so I think there's opportunities we can do from that edge of the spectrum as well.
So it'd be interesting if next year we do indeed have a symposium on computational photography around this time of year, if anyone will have made progress on that particular problem, which is having the software help recommend which of your photos are worth keeping. So with that, I'd like to close the today's sessions and thank everyone once again for coming.